So we can start with linear operators. So the calculus of finite difference plays an important role in numerical methods. Calculus of finite difference plays an important role in numerical methods. It deals with the variations in functions when the independent variable changes by finite jumps, which may be equal or unequal. So in contrast, the infinitesimal calculus deals with the relationships that exist between the values assumed by the function whenever the independent variable changes continuously in a given interval. So calculus of finite difference plays an important role in numerical methods. It deals with the variations in functions when the independent variable changes by finite jumps, which may be equal or unequal. In contrast, the infinitesimal calculus deals with the relationships that exist between the values assumed by the function whenever the independent variable changes continuously in a given interval. So that is the difference between infinitesimal calculus and calculus of finite differences. In calculus of finite differences, so the independent variable change by finite jumps. And in infinitesimal calculus, the values of independent variable change continuously, okay, in a given interval. So we can suppose that y is equal to f of x be a discrete function. So it means if it is a discrete function, so the independent variable changes by finite jumps. So if x naught plus h, x naught plus 2h, so on, x naught plus nh are the successive values of the independent variable x, where two consecutive values differ by a quantity h. So it means there are two values x and x plus h, or you can say that each value have a finite difference between the other values. So there is a finite difference between two consecutive values, and this finite difference can be measured with h, or we can say that if we add h in the first value or the one value, we can get the other value. So then the corresponding values of y are y naught, we can write like this: the corresponding value to x naught is y naught, and corresponding value to x naught plus h we can denote with y1, and corresponding value to x naught plus 2h we can denote with y2, and so on. So the values of the independent variable x are usually called the argument, and the corresponding functional values is known as the entry. Finite differences. So what is the finite differences? We can define as when a function f of x, which can be written as y is equal to f of x, is known explicitly, or we can say that suppose that a function f of x is defined explicitly or written explicitly, it is easy to calculate the value or values of f of x corresponding to a fixed given value. However, when the explicit form of the function is not known, it is impossible to obtain an approximate value of the function up to a desired level of accuracy with the help of finite differences. So as you observed in the previous discussions, so it is difficult to find a value with implicit formula or implicit functions, but in contrast with implicit functions or formulas, it is easy to find the values with explicit functions or the formulas. because in explicit function we have the clear value on the left hand side, and in the right hand side there is no value which matches the variable to the left hand side. So that is why to evaluate explicit functions easy as compared to the implicit function. First we can define the forward difference. So what is the forward difference? First order forward difference denoted by delta is defined as delta y is equal to delta f of x is equal to f of x plus h minus f of x. So it means the changes of the function at the point x plus h minus change of the function at point x. We can denote as delta y, the finite forward difference of y at the point x plus h and x. So here h is called the interval of differencing, or we can, in the previous discussions, we say that h is a step size. So here h is called the interval of differencing because the difference between x plus h and x is h. So if we add h in x, we will get the next point, which is x plus h. Second order forward difference operator can be calculated as, so to calculate the second order difference operator, just you can apply delta here, delta on f of x plus h minus f of x as you see here. Okay, so then we can write as delta f of x plus h minus delta f of x. And if you go back to this definition, it means so delta f of x can be written as f of x plus h minus f of x. And so we can get help of this one, and we can write delta f of x is equal to f of x plus h minus f of x. And we use the similar argument, okay, because here x is the same as we have x here. So just replace x with x plus h, and you will get this minus f of x plus h, and then replace this x plus h with x plus 2h. You will have delta f of x plus h. Or you can say, so the difference, finite difference of x plus h and the next point x plus 2h. As we have seen that what is delta f of x is the finite difference of the function at the point x and the next point x plus h. So similar argument we are using here. Okay, so delta square y is equal to, we can write as delta square f of x is equal to f of x plus 2h minus, this will be added because two terms are similar. So minus 2 f of x plus h, and minus into minus, it will become plus. So delta square y or delta square f of x can be written as f of x plus 2h minus 2 f of x plus h plus f of x. And similarly, third order forward difference can be calculated as, so we can just and apply delta another time. So here delta into delta square, it will be delta cube, and then delta into delta square f of x here. So it should be here uh, delta into delta square f of x is equal to delta f of x plus 2h minus 2 f of x plus h plus f of x. And now, so delta, because delta is a linear operator, so it can be applied on each term. So delta into f of x plus 2h minus 2 delta into f of x plus h plus delta f of x. Okay. So this f of x will be written again as we have done before, like this one. So delta f of x is equal to f of x plus h minus f of x. And this delta f of x, we have calculated here delta f of x plus h. So delta f of x plus h is f of x plus 2h minus f of x plus h. Here we can replace. So delta f of x plus h is equal to f of x plus 2h minus f of x plus h. And this delta f of x plus 2h we can replace with f of x plus 3h minus f of x plus 2h. So minus 2 f of x plus 2h minus into minus plus f of x plus h. So now we can simplify. So this f of x plus h and 2 f of x plus h are the similar terms we can add. So 3 f of x plus h. And here, so minus f of x plus 2h and minus f of x plus 2h are the similar terms, so we can add. So minus 3 f of x plus 2h. And so we can write as delta cube or delta cube f of x is equal to f of x plus 3h minus 3 f of x plus 2h plus 3 f of x plus h minus f of x. So similarly, delta 4y, delta 5y, and so on can be calculated. Forward difference in the form of binomial coefficients. So this forward difference can be written as in the form of binomial coefficients. How? Consider the following table as given below, keeping in view table 811. So forward differences can also be written as. So if the argument is x naught, so y naught is equal to f of x naught, and x1, y1 is equal to f of x naught plus h. For x2, y1 is equal to x naught plus 2h. For xn, yn is equal to f of x naught plus nh. Okay, how it can be written as delta cube y naught can be written as y cube minus 2y2 plus y1 minus y2 plus 2y1 minus y naught. So if you observe here, f of x plus 3h, so 1, 2, 3, 4. So here are 1, 2, 3, 4. So we can write 1, 2, 3, 4. So y3 is representing f of x plus 3h. Okay. And then there is a minus 3 f of x plus 2h. It will represent minus 3 y2. And then plus 3 f of x plus h, 3y1, and then f of x, y naught. So similarly, we can write delta 4y naught, y4 minus 4y cube plus 6y2 minus 4 y naught plus y naught. So if you just observe the pattern of these delta square, delta cube, delta 4y, so we can have a applications of Pascal triangle on the coefficients. Because if you observe that, what are the coefficients of delta square? The coefficients of delta square are 1, 2, 1. Okay. And coefficient of delta cubes are 1, 3, 3, 1. And coefficients of delta 4 are 1, 4, 6, 4, 1. So it is easy to write the coefficients of delta 5. We can add this 4 into 1, 5, 4 into 6, 10, 6 into 4, 10, 4 into plus 1, so 5, and then the last terms will have the coefficients 1, 1. So it follows the Pascal triangles of writing the coefficients. So that is why we can write in the form of binomial coefficients. The first coefficient is 1, so we can write as n 0, so then n1, n2, n3, so on, nn, and yn minus 1, yn minus 2, yn minus 3, so on, y naught. So where the coefficients, binomial coefficients can be written as n factorial over n minus k factorial into k factorial. So we can make a big table. If we have x naught, the first entry is y naught, and if we have x1, entry will be y1, and then delta y naught is equal to y1 minus y naught. For x1 is for x1, so this is a mistakenly repeated. So y2 is equal to delta y1 is equal to y2 minus y1. So this can be written as delta square y naught is equal to delta y1. So using this table, we can write this even fifth difference or delta 5. So delta 5 y naught is equal to delta square y1. So with the help of this table, we can write this delta cube y1, delta 4y1. So using landscape table, it is easy to calculate higher order desired forward difference. For example, delta cube y1, delta cube y delta 4 y1. Similarly, the backward differences. So first order backward difference denoted by nabla is defined as nabla y is equal to nabla f of x is equal to f of x minus f of x minus h is called the interval of differencing. So second order backward difference operator can be calculated as nabla square y, nabla square f of x is equal to nabla f of x minus f of x minus h. So nabla f of x minus nabla f of x minus h can be written as f of x minus f of x minus h minus f of x minus h plus f of x minus 2h. And so nabla square f of x will be equal to f of x minus 2 f of x minus h plus f of x minus 2h. Similarly, third order backward difference can be calculated as delta cube y is equal to delta into delta. So no, sorry, nabla cube y is equal to nabla into nabla square f of x is equal to nabla f of x minus 2 f of x minus h plus f of x minus 2h, and this nabla f of x then minus 2 nabla f of x minus h plus nabla f of x minus 2h, and then we can simplify with because nabla f of x is equal to f of x minus f of x minus h minus 2, so f of x minus h minus f of x minus 2h plus f of x minus 2h minus f of x minus 3h. Nabla cube y is equal to so f of x minus 3 f of x minus h plus 3 f of x minus 2h minus f of x minus 3h. Similarly, nabla 4y, nabla 5y can be calculated. So backward difference can also be written using the binomial coefficients, as we observed that nabla square y2 can be written as y2 minus 2y1 plus y naught, and nabla square y3 can be written as y3 minus 2y2 plus y1. Nabla square y4 can be written as similar nabla square y5, and nabla cube y cube can be written as y3 minus. So by observing these terms, we can observe the coefficients. So if this observe that here is the power of the nebula is same as the index of the y. So y cube and power of the nebula. So then y3, y2, y1, 2. This means y3 minus 3y2 plus 3y1 minus y2. So if you just observe, it also follows the pattern of coefficient is following Pascal triangle. That is 1, 3, 3, 1. And nebula, this nebula square y2 is 1, 2, 1. So after nebula square y2, we will go directly to nebula cube y cube and then nebula 4y4 and then nebula 5y5. So the coefficients of these operators are also following Pascal triangles pattern. So 1, 4, 6, 4. Similarly, we can write the next one 4 plus 1, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, and the last and the initial will be 1. We can write the next, the nebula 6, y6. Okay, the first coefficient will be y6, and then the next will be 5 and 1, 6. Next, 5 plus 10, 15. Next, 10 plus 10, 20. So next 10 plus 5, 15. So, and next 5 plus 1, 6. Next will be 1. So it is easy to write the next nebula pair. So that is why we can write in the form of binomial coefficients. That is nebula cube or nebula n by n. So there should be nebula n by n. So that can be written as n0 by n minus n1 combination binomial coefficient by n minus 1. So where this nk can be evaluated as n factorial over k factorial into n minus k factorial. And the next is the central difference. So central difference operator can be defined as delta. So this is the small delta. Y naught is equal to f of x naught plus 1 by 2h minus f of x naught minus 1 by 2h. And this will be delta y naught is equal to y half minus y minus half. And also we can write as delta y 1 by 2 is equal to y1 minus y naught. So, and next is the average operator. So average operator mu can be denoted by mu and is defined as mu f of x is equal to 1 by 2 f of x plus half h plus f of x minus half h, and mu y1 is equal to 1 by 2 y of x1 plus half h plus y x1 minus half h. So this implies mu y1 is equal to 1 by 2 y half 1 by 2 plus y minus half. Next is the derivative operator. So derivative operator is defined as df of x is equal to d by dx f of x is equal to f prime of x. And the second derivative, so we can apply this derivative another time and we can write is d2 over dx2 f of x is equal to f double prime. Similarly, we can write in the form of this power n. So it means nth derivative. So dn f of x is equal to dn over dxn f of x is equal to fn of x. And similarly, the shift operator. So shift operator is defined as and denoted by capital E. So shift operator E can be defined as E f of x is equal to f of x plus h. And if we go to the next order of the shift operator, we will write e to f of x is equal to f of x plus 2h, and en f of x is equal to f of x plus nh. So shift operator just shift the point to the next point. So